Hi, everyone. Welcome to the Power Hungry Podcast. I'm Robert Bryce. On this podcast, we talk about energy, power, innovation, and politics. And I'm pleased to welcome Simon Irish. He is the CEO of Terrestrial Energy. Simon, welcome to the Power Hungry Podcast.
Thank you, Robert. It's good to see you. Thank you for having me.
I'm glad to have you. I didn't warn you, but if you've listened to the podcast, I have guests introduce themselves. So I've given your title, but if you don't mind, imagine you've arrived somewhere and you don't know anyone and they ask you who you are. Go.
Well, thank you, Robert. So Simon Irish, Chief Executive of Terrestrial Energy. I was educated in the UK. I read a science degree, natural sciences at Cambridge University, spent 10 years in investment banking in London at a time when the big investment banks were looking for those with a quantitative education to run their complex financial models. I did that for 10 years and then moved to New York and was in the asset management industry in New York for 10 years before getting involved in the nuclear sector. A little bit by happenstance, Robert, actually. But I formed Terrestrial Energy in 2013.
So you've been at this now for 9 years. And I was looking back at my own records, and we talked in 2015. In fact, it's almost exactly 7 years ago. It was February of 2015. Now, I'm going to, as my brother used to say, bust your chops right out of the gate here. When we talked right. 7 years ago, you expected that you would have your reactor deployed 2023, 2024. Now, I am being a little cheeky here, but tell me what, I know it's very difficult to bring new technology to market. And we talked back then about why you domiciled Terrestrial in Canada. I'll ask you the question directly. So what's taken so long? And I'm with all due respect, what's taking so long?
Well, if you were to deploy a reactor system, there are other counterparties that need to be ready to deploy that reactor system. So whilst we are to some extent in control of our timeline, you have to engage with the regulator, and you also have to engage with the customer and financial investors too. So there's a natural pace that exists for the development of any innovation, any technology in any market. And we have spent the last 7 years very much focused on the regulatory pathway, engaged with private investors, and also engaged with probably the most important counterparty of them all, engaged with the utility sector, those that are seeking to use this technology. So that's what we've been up to for the last 7 years, Robert.
And so tell me where you are in terms of the and I want to talk about the integrated molten-salt reactor, which is your design. But tell me have you built a prototype? Where are you in now? I mean, if you blue skied it, and I'm, again, being cheeky off the bat here, but
yes.
If you blue skied it from now, then what's your best case in commercial deployment from where we stand now in early 22?
Well, maybe to your first point, in terms of what we've been doing for the last 7 years, we've been very much focused on probably the most important piece of the commercialization equation for an advanced reactor system. That's the regulatory piece, because without that, you have nothing of commercial value.
Sure.
You operate as a business. This technology operates in a very carefully regulated sector, and early regulatory engagement and progress with that engagement is so critical for the commercialization of this technology. So since we spoke last, well, it doesn't seem like 7 years ago, but since we spoke last, we've been engaged with we started with engagement with the Canadian Nuclear Safety Commission as part of their vendor design review process. And we started that formally, actually, started setting that up in late 2015, started that process in early 2016, and we expect to complete that this year. So that's been... we're in our 7th year of engagement, and we expect to have completed the full vendor design review process with the Canadian Nuclear Safety Commission by mid-year this year. So that'll be, that'll be nearly 7 years of engagement, and that is so important to the commercialization of this system, because it says a couple of things. Firstly, it says where you are with engineering. You can't take a reactor to a regulator. Regulators regulate nuclear power plants. In Canada, they regulate nuclear activities, and it's the activity of operating a nuclear power plant which is being regulated. So for us to make that progress in Canada, and we're engaged with the US NRC as well, we have to be designing a nuclear power plant, which is the product you sell. People talk a lot about reactors, but that's not really the product that's being sold. The product is a nuclear power plant that's going to be used for commercial gain with the in the hands of the operator, the owner of the operator. So we'll be completing the vendor design review. We anticipate that we'll complete that successfully, and we anticipate that in completing it successfully, we will have, in effect, the green light to move forward commercially. And that green light is a green light for those who are seeking to partner with us on the industrial side to move this forward at a greater pace, with financial capital that obviously wants to benefit from the successful scenario that green light employs, and also with customers, utilities, industrial users that are now seeking to use this technology in their businesses. And that regulatory green light is so important because it frames the first uncertainty with the technology.
Sure.
And that uncertainty is how you're going to regulate it.
Right. And so let me jump in here for a minute, because I'm very interested to talk to you now, because I just published a piece in Forbes about the NRC's rejection of Oklo's application. And Oklo, had an unusual design, a small 1.5 megawatt reactor, and they were just poured out. Now, the NRC said you can come back. But when we talked 7 years ago, and I thought it was interesting that you chose to domicile terrestrial in Canada because you felt that the Canadian regulatory regime was more flexible, I guess would be the right word, principles-based rather than rules-based. So walk us through that, because I think that now in particular, in the United States, this is I'm not an expert on the NRC, but I've watched it long enough to know that this is, as one Ray Rothrock has said, it's an uncontrollable risk. You don't know what this agency is going to do. So you made a conscious decision to domicile in Canada and seek Canadian regulatory approval rather than American regulatory approval first. Why?
Well, if you wind the clock back, this would be the thought process that was going on in the early days of terrestrial energy in 2012. We recognized that it was so important when raising private capital, and we're focused on raising private capital to support nuclear innovation that's been driven by an entrepreneurial private company. And we recognize that from a business plan perspective, it's so important that you're able to offer private capital a regulatory pathway which is sufficiently clear in cost and time. So
and you couldn't find that in the U.S.
Well, at the time in the US, we didn't believe that was competitive against the Canadian process. Now, a lot has changed in the last 7 years. You have certainly in the United States, there has been a lot of congressional interest on this problem. And the problem is a regulatory pathway that's clear in cost and time, because it's that pathway that stimulates the formation of capital, public and private, behind these exciting new projects. But in terms of where we were in 2012, we have to deal with the hand that was dealt to us by circumstances beyond our control. And we recognized there were certain unique merits about the Canadian process. It was stepwise, so you didn't have to step into it with $100 million. You could step into it with a phase 1, then a phase 2, and then necessarily a phase 3. And obviously, as you stepped into it, going through those capital gates, the commitment got larger and larger. But you did that because you became increasingly comfortable with the results you were getting. So it was a phased process, but it was also principles-based and risk-informed. And that means that created a degree of technology. The regulator was capable of being technology agnostic, because being principle-based and risk-informed, what that meant is the regulator had not written a rule book on the safety requirement for that system. What it had established a set of common principles that are common principles across many nuclear regulators that define generally accepted principles of nuclear safety today. And it was up to us to justify that our design during the vendor design review process met or exceeded those principles. And that was very important for us, because we're looking to commercialize a molten-salt reactor generation 4 system, and a different system in terms of technology that had previously been pushed into the commercial realm. So that
so if I can interrupt just for a moment, because I think this is key here in terms of this principles based versus rules based.
Yes.
Because in the Nuclear Innovation Alliance, they did a report on the NRC and permitting last year. Yes. NuScale, which is a light water reactor company here in the U.S., they spent over $500 million and 10 years to get their permit or to get their reactor design approved at the NRC, and 12,000 pages. Their application was 12,000 pages. So I'm making that point because how many pages of documents did you have to submit to get where, or how many have you submitted so far, and how much have you spent in Canada to get where you are today?
Well, I think that 12,000 pages is more an articulation of, if you are developing a nuclear power plant, you're down to the system level and you're down to detail engineering at a system level. How many pages of nuclear material, of engineered material, does that design effort cover? I think 12,000 pages is probably at least 12,000 pages. I mean, the position we're in at the moment is that we'll be completing what's called basic engineering. It's not particularly basic, but it covers all the systems associated with the operation of your power plant. And I'd say we are probably in excess of 12,000 pages ourselves, probably a lot, significantly in excess of 12,000 pages in terms of the engineering material. So that 12,000 pages is more a reflection on how much detail you need to create on the performance and the requirements of all your systems, such that you can go to a regulator and say, this is how it works.
Sure.
So, we're pretty much close to 12,000 page.
And so about how much have you spent then? Well, two questions. So how much have you raised overall? How much capital is Terrestrial raised? And how much have you spent on the permitting side, which I'm guessing is really the bulk of your spending? Where are you on that?
Well, Rob, we have been supported by private capital for the last since we formed the company. I prefer not to talk publicly about how much we've raised and how much we've spent, but needless to say that there's been sufficient capital raised to support a sophisticated engineering function that can take this design through the Canadian regulator and also engage increasingly with the US NRC. And in terms of
I'm sorry to interrupt, but so you're hoping that you get Canadian approval first, and then you can go to the NRC, or you're looking at doing a dual approval process?
Well, each regulator is sovereign, so you can't take a NRC approval and go to Belgium, for instance. You can't take a CNSC approval and go to the United States. And in terms of the vendor design review, it's an expressing a sophisticated opinion on the safety case of the reactor system. The NRC, and this is to some extent why it was so expensive for NuScale, what they sought is what's called a ruling. Namely, this judgment by the NRC is binding in a future license application. So the NRC is binding itself to some future point in time, a license application submitted by a utility. And it's binding itself to a decision that it's taken today during the design certification process that's been completed with NuScale.
Okay.
That is a much, much higher level of commitment from the regulator. The Canadian Nuclear Safety Commission says, we're expressing an opinion. This is a sophisticated opinion. This is based on our careful review on all aspects of this design submitted during the vendor design review process that's been going on for 6 or 7 years. But if there's a license application submitted for a license to operate this power plant, we're entitled to not change our mind, but to alter our opinion and alter our requirements. So you're not holding the regulator to a legal standard, which is the case for the NRC. The NRC has been held effectively to a legal standard. Once the commissioners finally, undertake their approval, law-making actions, on the design certification, then NuScale can go to a utility and say, this is now, if you submit a license to operate and construct on a NuScale power plant, in that submission, you can take this design certification because it is a binding conclusion.
So would it be fair to say that the Canadian process is more iterative then? You're iterating then as you go along, and then you go back and say, well, here's where we are now, and then it's not as hard and fast of a process, I guess. Would that be
well? Yes, it's you see this in other aspects of regulation, not just in nuclear regulation. In many aspects of regulation in the United States, and I have a cross-border perspective here, is very much rules-based. In Canada and elsewhere in the UK, there's sort of a concept of precedent and common law, which creates a degree of flexibility, but also perhaps in some respects uncertainty. Maybe a greater degree of commercial pragmatism on part of both parties. And that's reflected in the way that the nuclear at this stage, the regulatory process in Canada proceeds.
Gotcha.
So the degree of pragmatism will express an opinion. It'll be a thorough opinion, a detailed opinion, but it's not a binding opinion.
Okay.
It's not binding in licensing, and the NRC holds itself to a much higher standard and says this is binding in licensing. But if it misses something,
right,
then it's going to be it's going to be awkward because
sure.
Yeah.
So it's just, I guess the way to define it is that the hurdle in the NRC process is just higher. As you said, I was looking at my notes from 2015.
Yes.
You're just saying you thought there was just too much uncertainty. But let's talk a few numbers and to just get it back to the reactor design itself. So you said that you were looking to do your first plant in Canada. This was now 7 years ago. Tell me if this has changed. You said it would cost about $1 billion and that you had three designs. One was 80 megawatts thermal, which would be used in remote locations, and then 300 megawatts thermal, again, for industrial, and 600 megawatts thermal. So take a third off of each of those, right, for roughly to get the electrical output, right? Something like that, right? So 60 megawatts for remote. Are these still your estimates then, or are these still your designs that you're working on?
Well, Robert, that was at the stage where we had yet to start engineering, and at what was called the pre-conceptual design stage, we were still forming our product. So last time I spoke to you was definitely some time ago.
Yes, of course.
So we took one product into the regulatory engagement with the CNSC, and that's because the product is a power plant. You have to decide what your product is.
Right.
Our product is a 400 megawatt thermal reactor that's capable of net electrical generation of about 195 megawatt electrical.
Oh, okay. Uh-huh.
And the plant format was a double unit, so you have two of these things side by side, which creates a plant with nearly 400 megawatt electrical.
I see. Okay, I got my thermal to electrical conversion so it's about half.
Right.
If you have your megawatt rating on thermal, then you cut that in half roughly to get the electrical output.
Yeah, it's about 44%, which is excellent, actually. I mean, that is the great virtue of our system and Generation 4 systems, that this really expensive bit of industrial kit equipment, which is so costly and time-consuming to regulate. Once you've done that, you want it to generate as much many kilowatt hours as you possibly can.
Sure.
Because that's obvious. You generate, it increases your revenues.
Sure.
So in our case,
so that 44%. I'm sorry to interrupt, but that 44% on the efficiency, that you said that's high. Is it because your process heat is higher? You have high, and that means higher enthalpic efficiency. Isn't that the right word? Is that the case?
Thermal efficiency. There's another term there that I think is relevant. But the basic concept is high thermal efficiency, and that's critically important for economics. It's foundational with respect to the economics of any power plant, coal, or nuclear, or any machine, actually. In our case, we can operate at 44% net of the parasitic load of the power plant. And that compares to 30% for a nuclear power plant of the same size using water-moderated, water-cooled technology. So you go from 30% to 44%. That is an immense improvement in the industrial economics of nuclear power generation. I mean, that's why we're doing this.
Gotcha.
For that 30 to 44% gain.
So walk
Yeah.
us through then the integrated molten salt reactor. As I recall, you said this was a design that was developed in the U.S. in the 80s, and then now you've revived it. Tell me why walk us through, if you don't mind. I'm passingly familiar with these reactor designs, but there are a bunch of them. It gets complicated. Why is this better? What are the attributes of the IMSR
Yes.
relative to others?
Okay. So this is what's called the generation. This is part of a class called Generation 4. Generation 4, they're defined by international treaty from 2001. The US was a founding signatory, along with Canada as well, actually. And these are fission reactor technologies that are very different compared to the technologies that have been used commercially for the past, 60, 70 years.
The light watered reactors.
Yes, the light water-cooled, water-moderated technology. They were identified by this intergovernmental working group as the type of technologies that offered a pathway forward for the nuclear industry, a pathway defined by better economics, better fuel use, better performance, better waste profiles, etc. Basically, the future of nuclear. From a technology perspective, yes. Now, we're using a molten salt reactor, which is one of those 6 technologies that were identified in 2001. And we're using it because we think, our ambition as a company, our purpose, is to design a nuclear power plant with a set of technology and design choices to achieve a superior economic performance. But we're not doing this because we like molten salt reactors. We're doing this because we believe that our technology and design choices achieves a solution which is a very valuable solution to deliver to competitive energy markets. We think the problem today for many decades actually for nuclear power has been cost.
Sure.
It's too expensive.
And delay to get to market, right? And construction time. I mean, this is clearly playing out with Plant Vogel. I mean, and played out with the Summer plant. I mean, took forever.
Yes, and there's that problem is a problem of complexity, Robert. And complexity has a cost dimension to it as well. It has a time dimension to it. It certainly has a very negative impact on the economics and the incentives for those that you want to spend their hard-earned dollar to adopt new nuclear. It's a negative incentive because it's too costly, too risky, too complex, and the financing it requires a sovereign balance sheet. You have a technology today that requires a sovereign balance sheet to be deployed in competitive energy markets.
So, I'm sorry. Well, I like that. I like that phrase. But if you don't mind, what do you mean by a sovereign balance sheet? Tell me.
Well, you need the project itself, the infrastructure project itself, is so complicated and complex and so large that it can't be financed by private capital using any ordinary method. It can only really be financed by governments, where governments have, an extremely low cost of capital, and that cost of capital is essential if the project is going to take 10 to 12 years to commission and bring online and start generating revenues. So the incumbent technologies today require that the track record is they're sold by governments to governments.
Right.
That's not a particularly legitimate position for a commercial technology. I mean, if it can only be sold by governments to governments, it's going to play a very limited role in global energy markets. That's the problem to solve, and we're solving it with a Generation 4 reactor system. And Robert, the reason we believe we can solve it is going back to that first foundational statement I made, is that our machine operates 50% more efficiently than the incumbent machine. So just off the bat, your machine commercially is earning 50% more revenues.
Well, so let's talk about then that
Yes.
that issue then. So that higher efficiency, is that because you're processing the process heat, the design itself produces higher temperature steam? Is that part of the reason why you're getting higher efficiency?
Yes, I mean this is just basic thermodynamics.
Right.
Using a molten salt is thermally much more stable than water.
Right.
So what you can do, because of that high thermal stability, superior thermal stability, you can operate your machine at a much higher temperature.
So what is that, and what is that temperature?
In our case, it's 700 degrees centigrade. The reactor itself operates at 700. A water moderated, water cooled system, conventional technology probably can't get beyond 300.
Mm-hmm.
So your steam supply, in our case, it consists of very high temperature steam. In fact, virtually the same steam supply you see in a coal plant, about 585 degrees C and 18 megapascals in pressure. That's standard industrial steam, and that to drive a standard industrial turbine, and that means we can operate at pretty much the same thermal efficiency as a fossil fuel plant.
Ultra super critical, I guess, would be that right?
Yeah.
So then, tell me the cost then. So we've talked around. So we've got the design. You've explained the design on molten salt. Well, I want to come back to that, but so give me the numbers. So then you're talking about a 400 megawatt thermal, 195 megawatt electric. What's your cost to build? What are your estimates then to get this deployed on a per kilowatt basis or all plant basis?
Okay, so per unit it's going to be significantly less than $1 billion. A double unit, $1.5 billion, something like that.
So $1 billion for 200 megawatts electric.
Significantly under $1 billion.
Okay, significantly under, but so
I'll
just say less than less than $1 billion for 200 megawatts. But so
yes.
you're still competing with natural gas.
It's about on a pure cost basis, we think we can do better than $3 a watt instant overnight cost.
Okay, now we're
so
talking.
You can back into the number.
Okay, so $3 a watt. So compared to gas-fired turbines, maybe $1 a watt, depending on where you're building them, right? But your fuel costs are going to be less,
yes,
right? So that's the other part of the equation.
Yes, I mean you'll never compete on capital against natural gas, but in terms of the price of power, that's the levelized cost over the entire life of plant. Natural gas is a split. 70% is fuel cost, 30% is capital, and nuclear, it's probably the other way around. It's 70% is capital, 30% is operating and fuel. So maybe 80-20. So you won't beat natural gas on capital, but you'll definitely beat it once you've built it. You'll beat it on an operating cost basis.
Sure.
Yeah.
And so then what do you think then on per megawatt hour? What's your number then you think you can operate at?
We think this technology is capable of delivering electric power at 5 cents a kilowatt hour, $50 a megawatt hour. And that's before you incorporate any subsidy that you may get from carbon abatement credits.
Sure.
And if you just use it as a thermal plant, and I think, Robert, this becomes quite interesting now when you're looking at what's happening in the natural gas market after 10 years. We think this can dispatch thermal power at about $6 an MMBTU.
Okay. So for district heating or for industrial process heat or those applications.
Well, district heating is for sort of low grade heat that's not particularly exciting because there's lots of low grade heat that's left over from industrial processes. But our heat is high grade heat, and that has relevance. A lot of petrochemical processes relevant to green hydrogen production, green ammonia production, and if you have green hydrogen, you have the ability to make high quality steels that are green. The CO2 footprint is virtually removed from it. So that's the opportunity that you have with this double product, high grade thermal energy and cost competitive electric power, both of which is cost competitive and also near zero CO2 emission.
Sure,
that's important.
So blue sky it now, and I was cheeky to begin, in talking about where we talked about 7 years ago, but now we're here in 2022. Give me the blue sky estimate now. When do you think that you can get commercial deployment now, based on where you are in your development and all the work you put in, and where you've refined the design and now have one design that you're going forward with? What? Tell me, blue sky it. When will you get this out and producing juice?
Well, we think we can commission the first plant within a decade. So that's going to be by December 2031. Now, that time frame reflects the readiness of two other counterparties, Robert, and I mentioned this at the beginning of our talk today, the readiness of the regulator and the readiness of the utility. If both of those are ready to go today, and you may be able to cut a corner on a site that's got an early site permit, you may be able to also reduce that a couple of years as well to maybe 2028, 2029. But without, if you take that away because you think that's a bit too generous in terms of a timeline, let's say we're not going to deploy it on one of the few sites that has an early site permit, what is the time frame you're dealing with? A more generalized case, we think we could deploy this within 10 years. And I make that statement with respect to the United States, to Canada, and the UK, and perhaps other markets as well.
And are those the markets then you're targeting first? I would assume Canada would be your first market because that's where you would get your regulatory approval. You have need for high in mining and remote mining locations in northern Canada. Would those be your first candidates then? Where's your logical first deployment?
Well, we're increasingly moving forward on all three markets at the same time now. We focused when we formed the
UK,
business.
US, and Canada.
Yes, exactly. Yes, and that reflects, I think, the policy dimensions in all in those markets is very supportive for this type of technology. In Canada, I think there's perhaps a greater opportunity to deploy this system to support green hydrogen production, and also to support the type of industrial activities that have a very, very high energy load, thermal and electrical energy load in Alberta. I mean, that's a province in Canada with some substantial industrial activities that require a lot of energy. That's true for the United States as well.
Tar sands production, mining, etc.
Yes, exactly, and that's true for the United States as well. We are particularly interested in green hydrogen because, Robert, this technology, with this this double product of thermal energy and electrical power at near zero carbon, that double energy product, nuclear energy product, enables, we believe, the most cost competitive methods to create hydrogen.
So I see in looking at your thanks.
Yes.
I'm a skeptic on hydrogen, but that's a whole nother discussion. We'll leave that alone for now. But you have a pretty solid group of advisors, and your corporate industrial advisory board. I'm looking at this: Arizona Public Service, Bruce Power, which of course is the owner of Bruce Nuclear Station in Canada, which is the largest operating nuclear plant in North America. You got Dominion Energy, Duke Energy Northwest, NextEra, Engie, Ontario Power Generation. I mean, you've got a lot of potential customers right there. And then your advisory board, Ernie Moniz, you got a whole bunch of heavyweights on there. You haven't had trouble. Well, it appears you've had success convincing people that you've got the right technology, but you got to have patient capital as well. I'm assuming you have that. You don't want to talk about how much money you've raised, but you must have patient capital behind you to keep going this long, right? Because you're still a decade away.
Yeah, I mean, Robert, from a capital perspective, capital wants to see a return. Capital is the point of actually commissioning the first plant is not particularly relevant from a revenue perspective. Nuclear power plants.
I'm sorry. Why not? That's an interesting statement.
Yeah.
I hadn't thought about it that way. Why is that?
Because nuclear power plants are sold then built, not built then sold. So it's the vendor. We're selling the power plant. We're not financing it. The customer finances it.
Right.
So in that respect, you start providing services, profitable services, as soon as you secure that first contract with the first utility.
I see. So they're going to be paying. They're going to be paying you for the design right out of the gate.
They're paying you for site-specific engineering, which is required for the first. It's required so you can design your product for their site. So that is a service you're going to provide to the utility or the industrial customer. In terms of providing that service, we and others in the industry have kicked off that process. We earned revenues doing that last year, and they started the year before. So that's the path we're on in terms of developing our business, developing and growing revenues, and the revenue piece is the bit that's important for any business. So,
And you said you're already making revenue. You said some of your customers are paying you now.
We've engaged with utilities, and one in particular, actually, Ontario Power Generation, for site-specific engineering as part of their process to determine how our design could fit into their needs and their site. So that's a service that we're providing to a utility, and it's the type of service that we'll provide to any other utility or industrial user that is seeking to take this technology and use it for commercial gain at a location that at a site that they own.
Gotcha.
So that's the commercial process we're on.
And then I want to go back. I didn't let you finish on the molten salt reactor design, and that the salt being the thermal carrier for the reactor. And then, so explain what that mix is, if you don't mind. What is in that salt mix that's being circulated into the reactor and then into the powerhouse?
Well, the molten salt and the chemical form of it is pretty ubiquitous. It's a pretty standard, industrial salt. But in that salt, you actually put uranium fluoride, a uranium salt.
Right.
And when you heat it up, it effectively looks like water. It's got a slight bluish green glow to it, but it's just translucent, completely clear. Now, the virtue of that, from a safety perspective, because that has a cost dimension to it as well, and an economic perspective, is that you can operate hot, but you also, from a safety perspective, you have a mechanism which is extraordinary in its capacity to dissipate heat. Fluids, particularly thermally stable fluids, move heat around and dissipate heat naturally by convection. You can't turn that off. You can't. There's no fan belt there to break. It's a inherent behavior of the system, which is a law of nature. So fluids, if fluids convect, and that's important with respect to removing that intense heat of the fission process. Nuclear energy is associated with an intense amount of energy being created. It's characteristic, whether fission or fusion. And what you want is a system that is capable of dissipating that heat under operating conditions and accident conditions as well, always dissipating that heat, where you have a cooling system that's always on. And the virtue of a molten salt is that if you create conditions where you fission that uranium in this super thermally stable fluid, that heat will naturally and always be dissipated, within the reactor vessel, and you can't turn that cooling system off. It's a natural property of the system itself. So a virtue you have of molten salt reactors, not only because you've got a thermally stable coolant, but also you've got a liquid fuel, is that you can incorporate into your design these very important characteristics of inherent and passive safety. And those two characteristics, inherent and passive safety, they're not just super important for economics because it simplifies your engineering effort and your engineering challenge, but it's also super important for social license as well. That is part of the attraction of using a molten salt reactor as we pursue our mission as a company to transform the price of nuclear power generation.
I'm glad you brought that term up, the social license, because that's one of the issues and one of the key hurdles. As I've been writing and talking about natural gas and nuclear energy for now more than a decade, and saying if we're serious about CO2 emissions, we have to be serious about nuclear. But the big hurdle, it seems to me, is that social license and that education of the public to say, no, we're different. So walk me through that. I mean, if you were on television or or just give me the pitch then. If you're talking to a lay audience, a general audience, tell me, you've given me the technical part of this, but sell me on this, that no, we're different and you're going to like it because of why. What's the pitch you're going to make that is the one that's going to change people's minds, that gives you that social license to operate?
Well, the social license, when we formed the company in 2013, Robert, that was really important. But we've moved so far on the social license point. I don't think social license is a major impediment for nuclear innovation. in Europe, in the UK. Well, I'll just say UK and leave Europe out because it's a patchwork of different,
it's complicated.
It's complicated, yes. And certainly in terms of social license in Canada and the United States, nuclear is now viewed by anyone who wants to hold a credible position in their commentary of the energy challenges facing us. And nuclear is viewed as an essential part of our energy mix. So the social license exists. It's been expressed with a very impressive trend line in nuclear, supportive nuclear policy in Canada, United States, and the UK. In some jurisdictions, it's still a problem. For example, Japan, given their recent experiences, social license for nuclear. I think social license for conventional nuclear, water-cooled, water-moderated, boiling water reactors, that type of stuff is still very, politically very awkward. But social license, particularly local social license around a nuclear power plant, Robert, it's those local communities who understand the technology that are very supportive, probably some of the most supportive communities for nuclear power. And if you look at polls that have been published recently, then you see a very healthy movement towards an increasingly supportive attitude amongst the man in the street and the public square towards nuclear energy. One other point that that's quite an interesting point is I think for some people, the social license question, it sits in what I refer to as this paradox. I call it the neighbor problem. And the neighbor problem is you have a pollster who's going down the street asking people what they think, and he knocks on number 10 of whatever street. Door opens and he has a chat to the guy who opens the door, and he says, "What do you think of nuclear?" And he says, "Well, I love it. I really do. Fantastic. That's what we need to move forward with a sort of prosperous, into our prosperous energy future. The problem is my neighbor, he doesn't like it." So the pollster goes to number 11 in whatever street and knocks on the door, and the door opens, and he asks the same question. He said, he goes, "What do you think of nuclear?" And the pollster goes, what do you think of nuclear? And the chap who opens the door goes, "Well, I love it. It's our future. We must get on with it. But the problem is my neighbor in number 10.
The neighbor doesn't like, yeah, right, yeah.
So I think that's the social license paradox, frankly, for nuclear today.
Well, I think it's interesting what you said there about the issue of that the social license for light water reactors has been revoked. I'm putting words in your mouth here, but because you have a new chemistry, you have a new story, and therefore you have a different social license. You have the chemistry gives you a different story, which gives you a different profile in terms of the social license. Is that
you have economic legitimacy, I think is the way to put it, Robert.
Economic legitimacy.
You have a nuclear power plant and technology that can be supported through the ordinary means of industrial development and construction and operation. And it doesn't need to be pushed out into markets by government mandate, because the technology is so marginal in terms of its economic capability that it could not be supported without massive government support. So what you have with nuclear innovation in terms of social license, I think you have economic legitimacy, and that's what we think we can deliver with our IMSR.
So the economic legitimacy comes from your ability to finance this with private capital, without having to have the government pushing this. So you don't need the government of Abu Dhabi to hire the South Koreans to build the Al Baraka plant. You could do it.
And the government of Abu Dhabi, I'm sure they've got the cheapest source of cost of capital in the world. They've got the highest quality credit.
Right.
So they are exceptional in the investment world. So obviously that project looks very different to them compared to an industrial that doesn't have that access.
Or Pedernales Electric Cooperative here in Texas, or some other one that's going to be. So then tell me about the U.S., Canada. You have a footprint in both markets. I was just looking at your website, and you have one office in North Carolina, and then you're in Ontario. I've forgotten you're outside of Toronto, right?
Yes. Near Pearson Airport, yes.
So
Yeah.
So tell me why you need it. You need both. You need a foot in both markets. But I didn't quite follow how you're pursuing the licensing initially in Canada, but you're also talking to the NRC. Tell me what you're doing with the NRC relative to what you're doing with the CNSC.
Well, we started with the Canadian Nuclear Safety Commission,
right?
And a couple of years later, we started pre-license application discussions with the US NRC, and that was very much in our interest, because we're seeking to deploy the system as quickly as we possibly can in the United States. Rule number one, as you go down that commercial road, is early regulatory interaction. The regulator has to be prepared, has to understand, has to, before that application, way before that application arrives, it's in your interest to ensure that the regulator is prepared for that application, understands the technology, and part of that process is associated with the submission of white papers, topical reports. There's all manner of activities that can be undertaken as you work with the regulator well in advance of submitting that important license application. Our engagement with the NRC has been leveraged, I'd say, by an initiative undertaken by both agencies in summer 2018, where both agencies sought to collaborate.
CNSC and
the US
NRC, just to be clear. Yeah.
Sought to collaborate on the methods, practices, frameworks, methodologies to efficiently license these new reactor systems, these Generation 4 advanced reactor systems. So the NRC has a strong interest in getting prepared. It's getting prepared because it's working with other regulators, not just the CNSC, but it's working with the CNSC, and we're engaged with the CNSC in Canada in an advanced way. So it allowed us to engage with the US NRC to leverage our activities in Canada, and there was very much a mutual self-interest there. I mean, we were very pleased to support that initiative because we saw it in our interest too, that the NRC was moving forward as quickly as possible in getting prepared for that future license application that we've started that strategy, that planning strategy already.
And so when do you think you would then make a formal application to the NRC? Would you get an opinion from the CNSC first? Would you wait for that before you go to the NRC, or would you do it on a dual track?
I think we want to get that that commercial green light. The CNSC has been looking at this power plant design for it's in the 7th year. We want that commercial green light in the summer, and at that point we will be moving
this summer, this year. You're hoping to get it that after 7 years that you would get that green light. Is that the term of art is an opinion from the CNSC? Then is that the
it's a completed vendor design review, at which point they express a very detailed opinion on the licensability of this power plant.
And I'm sorry, you said the vendor design, right?
Yes.
Okay, yes. I just wanted to make sure.
So we're facing off as the vendor,
right? Yeah.
To the regulator. We're not facing off as the license applicant. That's going to be the utility, right, that would be seeking a license to construct and operate.
Sure, which is a separate issue from what you're seeing as the vendor, right? But that term of art is the completed vendor design review. Review, right? Yes. Okay, yeah, okay. And so you want to get that by this summer, and then you'd go to the NRC and say, "Hey, look, we got this."
At that point, we would be seeking to submit, and this is public record actually, although it's not necessarily that easy to find on the NRC website. But we are seeking to apply for a standard design approval of the most innovative element of our power plant design, and that is what's called the integral molten salt reactor core unit. That is where the innovation sits, the molten salt reactor sits itself. So that's the next stage of our engagement with the NRC. It's a standard design approval for a substantial proportion of the power plant. And that's the innovative piece, the molten salt reactor piece at the heart of that power plant. The reason we've done that, Robert, is because what's exciting about our design is, on the one hand, what's new and what's different and why that's exciting. But it's also what's interesting about our power plant design is what's not new and what's not different. So we've been laser focused in selecting innovation that achieves our purpose. And if innovation does not achieve that purpose, we stick with conventional processes, components, methods, practices. So our licensing strategy, regulatory strategy in the United States is to focus on the novel piece, because we don't believe that the standard piece represents a unusual set of regulatory uncertainties.
You want to show them. You want to show them things that they're familiar with and that they.
And so, at a later stage, you'll come back to that to this piece and say, look, this is just standard in the industry, and we'll submit that piece later. But the novel piece, which is the reactor itself, we'll submit that, and that's going to be the first step of our formal engagement, licensing engagement with the US NRC. And just on this point, Robert, about being very careful about where you innovate, because nuclear innovation comes at a cost, financial cost, time cost. Be very focused and clear as to why you're doing it. Okay, so we're doing it for economic gain. But case in point is that our system uses standard nuclear fuel,
right?
Because that's understood.
So low enriched uranium.
Well, also standard assay low enriched uranium,
okay,
which is the standard industrial material that's used in civilian power plants across the world today. There's an industrial complex, big, very expensive industrial complex that's been put in place to enrich, manufacture, supply, transport that material to countries operating civilian nuclear power plants. We want to, in deploying our system in commercial markets, we want that system to be able to inherit that supply chain capability. So we're using standard assay low enriched uranium.
And that supply chain is, you can depend on that in Canada, right where you are, right? You don't need to go outside of Canada to.
Yeah, I mean, Canada doesn't use enriched fuel. It's quite unique. It uses.
Okay.
But
right.
we could go to Europe, United Kingdom, France, and potentially the United States for standard assay low enriched uranium.
Sure. Okay.
As the fuel for our reactor system. That's how we're going to source fuel. But fuel is, unless you can point to a secure and reliable long-term supply of nuclear fuel, it's going to be very difficult to find a utility that's going to commit a lot of capital
to
operate it, where the investment case is based on reliable operation for at least 30, 40, 50 years. I mean, you have to, in terms of that duration, you have to get all other aspects of the project to match that certainty, including fuel supply. So we that's part of our pragmatism, actually.
Sure. Well, I think that's an interesting, that's a key word here, right? Is that certainty issue that, you've been dealing with these uncertainties in terms of licensing. And as I mentioned, Ray Rothrocker earlier talked about this uncontrollable risk around the regulatory part of this, that I think I'm very hopeful for Terrestrial and a lot of these other companies, but it's just the uncertainty in this getting from the concept and the paper reactor to the commercialization. It's just been, companies fail left and right in that, what is the technology valley of death. But let me ask a specific question. So what's your head count then at Terrestrial? How many people do you have on payroll?
We have our team at the moment moving the project forward about 120 at this stage.
Okay. Yeah. And who are your biggest competitors then? I know that there was Bruce Power, forgive me for not looking this up right before we got online here, but there was a competition, was it Ontario Power Generation or to select a new reactor? But you were in the running there, and I'm not, but you weren't selected, right? Was that a big blow? Who was selected? Who are your biggest competitors?
Well, I think you're referring to the OPG down selection, and that got a lot of international attention.
There you go. Thank you.
So Ontario Power Generation, probably for the last 3 years, had a program, it's just been concluded, had a program to select a small modular reactor technology to deploy at its deployment-ready site at Darlington. And they had started a process with a wide catchment, pretty much every SMR technology available on the market. And through a sequence of down selections, they got down to 3 in the summer of 2020. So for that 18-month period from summer 2020, the end of last year, they worked intensely with 3 developers of SMR power plants. Those 3 were ourselves, Hitachi, and X Energy, 2 generation 4, 1 generation 3. Their objective was to the greatest extent they could have a project where you're delivering one of these power plants in 2028. That was a very important objective, and they made their decision at the end of this year, and it's for power generation only, to supply move forward with the next phase of their project with Hitachi, and that's a small boiling water reactor. So they were strongly attracted to 50 years of operating experiences with boiling water reactors, and that created the certainty that they required in pursuit of their 2028 goal. So we didn't move forward with Ontario Power Generation, but the market for these technologies, Robert, is immense, particularly Generation 4 technologies, where the market for clean heat, thermal energy, and electrical power generation is extensive. It's not just one utility in one province in Canada. It's many utilities and many industrials across many advanced industrial economies, and that has always been our marketplace. So we're moving forward with other relationships, and we want to be focusing more on the thermal energy as well as because that piece is unique to the Generation 4 technology class. The Generation 3 technologies can't compete. They don't have the technical capability of delivering high quality heat. So we want to be moving forward with the high quality thermal energy message that's very relevant to chemical production, petrochemical production, supporting natural resource extraction, beneficiation, even steel refining as well. So that's the lane that we are increasingly focused on at this point in time.
Sure. And that well, then is it fair to say then, since you were in the running directly with them, X Energy and GE Hitachi, I mean, those would be the ones that are your biggest competitors now, or your ones that you've got. I mean, it's a crowded field and also kind of not crowded too. I mean, so who do you are these your main competitors?
Well, and certainly in terms of that procurement, yes, we're competing. In that that small playing field in southern Ontario. The last 18 months, we're competing with Hitachi and X Energy, but there's a much bigger playing field here.
Sure.
And it's supplying clean, cost competitive energy to many industrial users across many industries, and that is a really textured patchwork of different users wanting energy for different purposes. And this idea that this is somehow internet search where the winner picks up everything that's just not the way the energy market works.
Sure.
So we're focused on what we think are particularly interesting points for us in particular areas, and that's our strategy moving forward.
Sure. Yeah. Let's talk about China for a minute. And we've been talking for about an hour. And again, my guest is Simon Irish. He's the CEO of Terrestrial Energy. You can learn more about them at terrestrialenergy.com. The piece I wrote recently for Forbes about the Oklo being the application being rejected by the NRC. To me, it was just there were a lot of things that were interesting about it. But one of the key things was that just a few weeks before that license was rejected, the Chinese began operating a high temperature gas reactor in Shandong province. Are the Chinese just miles ahead of us? And if so, why?
Well, the Chinese have got a horse in every technology race. So they're going to say, we're not going to decide which is going to be the commercial winner. We're going to do everything. And that's in the high temperature gas reactor side. That's what they've done. They've turned a high temperature gas reactor on, and there was an announcement, I think, before the end of the year on that. It was interesting for them because they were obviously very pleased with that engineering effort, but they also did recognize and did comment that commercially this doesn't look too exciting because the technology is demonstrating that its characteristics economic characteristics, put it in a box where it's going to be more expensive than conventional technology. So it's not particularly clear what the commercial value of that project is, but they've got a prototype commercial plant, and the West has had prototype commercial plants of the same character, high temperature gas reactors, and they haven't been particularly commercially successful either. So, but China is committed. They're not trying to pick, and this is if you are to compete with China, you have to recognize that it's got a horse in every race, despite its clear engineering and technological sophistication on the nuclear front, and its determined policy as well, political ambition. It's not trying to pick a technology that's the winner. It says, we're going to invest in nuclear innovation across they've got a molten-salt reactor being developed as well, across all these lanes. And that is how we are going to guarantee our future superiority, not just in our regional market, but presumably they've got aspirations for global superiority of Chinese technology in the advanced reactor space. They're not picking a winner. And in terms of innovation, I think it's very, very important from a policy perspective that policymakers don't try and pick winners and take it upon themselves, the role that's usually left to private markets, to select the winner. The history of nuclear innovation today in the West anyway is not a particularly attractive one when you look at the efficiency of the process of nuclear innovation. It has not been left to markets to decide. Well, it is now, because the incumbents are largely going bankrupt. So the market involvement in the West today is to hold up the stop sign, which is the stop sign associated with bankruptcy of those pursuing incumbent technologies. But
you're talking about Westinghouse here.
Yes. But the go sign, which is the go to private capital, the go to private industry, policy has to put themselves in a situation where they're holding the go sign up. Now, China is not particularly worried about that green go sign, because its policy is to invest in every single system. But therein lies the key as well. I like the way you've described that. But they're building 46 reactors. So the Bloomberg's latest report is 46 reactors. Should be a wake up call.
They're stealing a march on the U.S., on Canada, the rest of the world. They're burning a hell of a lot of coal too. They're record consumption of coal. But the Chinese are building 46. We're building 2. They're at Plant Vogel. They're over budget, over cost, and the Russians have deployed the power ship and PVEC in Siberia. They're forging ahead. But is that because of? Going back to your idea about the sovereign balance sheet, is that a direct result of the fact that the government has a direct role in the development and deployment of nuclear in those two countries? Is that the main difference?
Well, they have a direct role in the innovation in any industrial sector, and it's particularly pertinent in nuclear. It's very clear that direct role in supporting innovation in wind and solar had profound consequence with the speed at which you got innovation in that sector going back 15 years. Now, there's an argument to said to what you got from all that policy today. But it's undoubtable, irrefutable today that policy commitment held up a massive green sign to private capital and private industry to get going and commit capital to innovation in that sector. That's undeniable. Nuclear needs that green sign.
To be clear, you're talking about wind and solar, that they had the government stamp of approval. So yes, go ahead. Go ahead.
Yeah, and it was real policy support, which had an effect on capital formation around innovative projects in that space. That green go sign was there, and it had an impact. We need that green go sign, because the nuclear industry today consists of 2 lanes. It has a lane associated with those that are seeking once more to continue with the commercialization of incumbent technology, and you've also got a new lane that's been created. And this lane is the young entrepreneurial growth company that it thinks that it, with a very, very focused business plan, can do so much better with respect to design and technology choices and create a much, much better product. Okay, that is the grassroots of nuclear innovation today, and its policy needs to support innovation at those grassroots. So that's the I think that's the important dimension, intersection between what's happening in the private side and what's happening in the policy side. Governments have gone a long way to support this in terms of grant funding and grant activities. So there is policy support, but it needs to accelerate, and it needs to have the same outcomes as we saw with wind and solar 15 years ago.
Right.
I mean, that was a big green sign, go sign. One other point as well, Robert, and it was a rather long, lengthy answer to your short question, but is that nuclear is, because it is so heavily regulated for good social reason, that first plant requires a much greater degree of financial support. So you have this paradox that the first plant requires government support because of its uncertainties, sure, because of regulation. But the second, third, and fourth, and fifth can never happen without the first. But the trouble is, the second, third, fourth, and fifth will only happen if private sector, if it's meaningful for private capital. So you have this risk that you create stranded technologies.
And the bet is $1 billion. I mean, that's what I've heard from Thor Kahn, from Robert Hargraves. They have a different, they have a salt reactor that they want to do in power ships. But you've both given me the same number. You need $1 billion. I mean, you got to have a stout investor that's willing to say, oh yeah, well, here's $1 billion.
Well, you need an investor that's price sensitive in pursuit of an opportunity. So yes, you need an investor that recognizes the commercial opportunity from adopting this technology and deploying it, which goes back to that green go sign, because there were some strong incentives to adopt wind and solar 15 years ago in terms of tax incentives, etc. Those incentives, I think, can apply to nuclear and the nuclear industry and can have a similar effect.
And so you're going to need the tax credits. I mean, this is what's been driving wind and solar.
It's driven innovation in a lot of other industries.
Yeah,
it works. Production tax credits, incentive investment tax credits. There is a policy framework that exists today, and I will say, Robert, that it is growing. And the good news is that the trend line is extremely encouraging. We're participating in some of this as well.
But it needs to go faster.
Well, if you think China's the competition, you've got to realize that there is you've got to make the innovation cycle in open, competitive Western markets move faster.
Sure.
Yeah.
So just a few more questions, Simon, and I appreciate your time. I'm glad to catch up with you now, seven years later. Tell me, what about the industrial base, though? Because this is the other. I mean, you've got the regulatory, you've got the technology, right? And it seems like it's very viable. You've got the regulatory issues, which you seem like you've got a pretty good handle on, but now you have to make it, and you have to make not just one, you have to make a whole bunch. Mm-hmm. And this is one of the issues that I think has been haunting the large reactor space, right? Where you've got to have the forging capabilities, and there's only one place in the world, or Japan has one in the.
Yes.
So how do you scale this? And then I've got just a couple more questions to sign off.
Well,
how do you make sure that you have the industrial base available and the manufacturing base that you can scale, and you can not just build one or two, you can build 200 or 300?
Well, it starts becoming more important when you're talking about the type of pressure vessels that are essential for traditional reactor technologies.
Sure.
Because we're left in a world where there are only about a couple of suppliers that you can engage with, and I think they're in Asia at this point in time. That's not a fact of conventional reactor technology. So our technology, we don't have. Our reactor vessel doesn't operate at 160, 170 atmospheres. It operates at effectively atmospheric pressure. So it doesn't require that level of ultra sophistication with respect to steel forging. It's a more standardized industrial component.
Sure.
So because it's more standardized, we think again it's more scalable with existing industrial infrastructure that exists in the United States and elsewhere.
So that's
Yeah.
so that we hadn't talked about the pressure issue, but yeah, that's the key, right? If you don't have, if you're operating at high temperature but low pressure, so you're not going to necessarily need some super sophisticated manufacturing base because of that. I'm trying to simplify
Yes.
that, but is that a fair assessment?
Yes, I mean, in terms of major component procurement, and this shows where we've got to with commercialization. We're not out there announcing MOUs. We have the last 18 months in pursuit of deployment with OPG. We were announcing contracts for major procurement, for the procurement of major components for our power plant. We are going to get our steam generators from Siemens. We're going to get our industrial pumps from KSB Pumps in Germany. We're going to get our fuel from Arano and Westinghouse in Europe, and so forth. So the attraction about this design is that we seek, and we think this is very important for our commercial mission, is we seek to use as much as existing industrial capabilities as we can. It's obviously true so important on the fuel side, but it's true with respect to where you're going to get your steam generators from, where you're going to get your pumps from, where you're going to get your reactor vessel from. So we are working with suppliers now for procurement of those major components.
Off the shelf components, I guess would be.
Well, it's nice if they can be totally off the shelf, but certainly the counterparties that we're engaged with have the capabilities of customizing their existing products to meet our needs, and that customization is really valuable with respect to steam turbines, because for a conventional reactor system, particularly a boiling water reactor, the steam turbine is hyper customized to the needs. That's a nuclear component and regulated as such. Our steam turbine is a standard industrial component, not a nuclear component. So that's a benefit for us with respect to sourcing these components, not just for the first plant, but being able to repeatedly source these components for second, third, fourth, fifth, sixth.
Sure.
Yeah.
So last couple of things, Simon, and these are questions I ask all my guests. So what are you reading? I'm sure your job keeps you quite busy, but surely you have some books on your nightstand or on your desk. What is keeping you busy when you have time to read?
Well, I've picked up Alvin Weinberg's autobiography.
Aha.
And I've read it. I read it, and that is sort of part of the happenstance going back to 2011 and 12 in terms of how I became involved in the nuclear sector from Wall Street, and the first time I read it, it allowed me to answer the question, if molten salt reactors were so good, why did they stay behind the curtain at the national lab level for half a century? Why did they not burst out? And his account of the history of innovation in that first nuclear age is very insightful, because the nuclear innovation room, Robert, is very noisy. You would think that the only noise you hear is the clamor from industrial users to say, we want the cheapest, the most competitive energy source you can supply. But the nuclear room in the first nuclear age, and even this nuclear age now, is there's a lot of chatter in different directions. Political chatter, a lot of political noise, geopolitical noise from the incumbents that want to maintain their position in industry because they have a very close relationship with government that has served their shareholders well for so many years. So that is the nuclear innovation room. It is very noisy. And Alvin Weinberg, and the reason I pick up his book again is that you need to understand that if you're going to move forward with your innovation. You need to understand the motives, the voices in the room, and learn from history.
Right.
Why did the molten salt reactor not blossom? It was a tremendous technology. And Robert, I think there's an answer to that. It's a political answer, not a technology answer.
And it's a what answer? I'm sorry?
A political answer, not a technology answer.
So it was a culture issue.
Yes, there's a political dimension to it as well, but it wasn't a technology. It wasn't because it was a technology that was technically inferior. That wasn't the reason.
It was the politics of anti-nuclear,
Yes.
Yes. It's interesting you say Weinberg, because one of our other guests, Eric Meyer with Generation Atomic, Weinberg is one of his personal heroes. So any other books before I go? I ask you the last question?
Yes, the other one is How Innovation Works by Matt Ridley.
Oh, sure, yeah.
And I like that because I think...
And why it flourishes in freedom.
Yes,
right? Yeah.
exactly.
Yes.
Yeah, and that's, I've only just picked that up, but I like, Matt is academically qualified to apply sort of evolutionary algorithms that he's gained from his PhD study of biology, and apply those algorithms to how innovation actually works in in an open economy. And I think those observations are fascinating.
Yeah. Matt's been on the podcast, and I've been on the podcast twice, I guess. One for How Innovation Works, and then for his latest book, Viral, which is also quite remarkable. A great, really a fascinating read about the origins of the pandemic. So, my last question. Yeah. Go ahead, please.
No, that's probably my next read, actually.
Yeah, I recommend it. Also, Greg Easterbrook was on the podcast. His book, The Blue Age, is quite fascinating about the U.S. Navy and the history of maritime history. So I also asked my guest, Simon, what gives you hope?
Human ingenuity, Robert. In terms of hope, as a businessman, I prefer optimism as a word. What gives me optimism? There's a great phrase from Wall Street, which is from my days in London, New York, which is, there are only two hopes in this world: Bob Hope and no hope. Hope is not a business strategy. But what gives me optimism? And what gives me optimism is the power of human ingenuity. And we live in a time when, in many ways, in many industrial sectors, human ingenuity is delivering some absolutely fantastic innovations, and that power, that spirit, gives me great optimism as we look to build a business and build terrestrial energy.
I like that. I guess maybe what makes you optimistic instead of hope? Now you may have made me change my closing question. The late Molly Ivins, I've used her line many times. I'm optimistic to the point of idiocy was her line. So anyway,
that's a good quote. That's a good response.
I'm the same way. So Simon Irish has been my guest. He's the CEO of Terrestrial Energy. You can find more about his company at terrestrialenergy.com. Unless you have something else, Simon, I'll thank you for being a guest. It's been great fun talking to you.
Well, thank you for having me today, Robert. Enjoyed our discussion. Thank you.
Good. And all you out there in podcast land, tune in for the next episode of the Power Hungry Podcast. And until then, see ya.